So we can model our transmission line with a familiar model. A resistor, an inductor, and a capacitor. So this is where we're going to send in our step function. And this is where we're going to put our microcontroller and catch the signal, the step function. So this is going to go in here. There's going to be a little bit of resistance, so we're going to have a current limitation. There's an inductor, so the current is going to lag, but this is also going to charge up and kind of keep the current from disappearing right off the bat. This is going to lag the voltage. So let me just draw an axis like this. So the voltage is going to hit this and hit this right away, and it's going to start lagging here. So we're going to see a voltage lag like that. It's going to reach the level of the step function, and then when the voltage goes down, we still have current here that needs to go somewhere. So as our microcontroller complete the loop like that, so our voltage is going to travel, it's going to start lagging here, so we're going to have this lag here. Yeah, it's going to draw the current like that. Then when we shut off with this part of the step function where there's zero voltage, we still have voltage here, so it's not going to immediately go down to zero. And if you can recall, this is our slope on our node here, and it depends on the current divided by the capacitance. So the higher the capacitance, the smaller the slope, so the slower it's going to charge up. The less capacitance you have, the faster, the steeper the rise time, the higher the slope on the charge rate. So if this slope isn't fast enough before the step pulse turns off, so let's say we're at a kilohertz here, a kilohertz signal, so this is 1 milliseconds on, or 0.5 milliseconds on, then you will get this type of wave here, because it'll charge up, and then before it can charge up, let me draw that in red, so you might get behavior like that, like that. And this might be too low to register for the microcontroller as a high. So that's why the capacitance is so important on the line. And the smaller capacitance you have, the higher frequency of signals you can put on that line and still keep the integrity of the signal. And if we look at an example, step response example, let's just say the red curve here, we see a lot of ringing and oscillations, and these oscillations are going to induce current on adjacent lines. So if this ripple is too high or too strong, your entire circuit board might suffer. So we can expect a kind of slope like that. Now if you remember, this thing kept current, so that current is going to add, and the voltage we're interested is on this node. This is our output receiving node. So current's going to go in and through those two places. And this is where we get ringing. It's from the play between the inductor and the capacitor. So if these two parameters are not matched, we might get some ringing here, and our wave might end up looking something like that instead. This is, I think, impossible to avoid on a circuit board, because there's always going to be noise and crosstalk and inductances and capacitances. But as long as we get over the threshold and our receiver can acknowledge this one bit as high, we're in the clear. So we can do voltage division on this node. So it's the input voltage that we're putting in times, let's plug in the impedance for a capacitor, is that right? Okay, and let's simplify this further. Let's do a common denominator. Let's clean that up a little bit further. These two cancel out, right? And we're left with 1 over This is our transfer function. This is what our input has to go through to get to the other side. So this is our input, step function. This is our system. This is our output. So this is going to be our step response. Okay, so this is what we ended up with in the end. U of t, which is 1 when the time is on, becomes 1 over s when you take the Laplace transform. So we now have 1 over s, and it goes in through our system, and we get our output. And we just have to multiply that out, and that gives us this expression. Now we can do the inverse Laplace of this to get back to the time domain. The ideal function with example, right? And we can see the ideal black line here. This thing has steady state error. It has some oscillations, some ringing. It has a little bit of delay. It has a slope here. All of these things are very important when you're analyzing a circuit and when you're sending digital information on a line. So we're going to be looking more into that later in the next lesson.